All right, welcome back to part 2 of our exciting day here on February the 15th, the day after Valentine's Day. Day after Olivia made a boatload of money at Amori last night.
Did you go to Amori?
I did not go to Amori. I went to the club.
The pub? Oh,
The club
Okay.
in Homewood. It's a members only restaurant that there was a party that I was invited to go to.
That's cool.
Okay, it was actually Dr. Harmon's anniversary party, and so she got married on Valentine's Day.
Have you ever been to the Anvil?
No.
Neither have I.
Okay, so notice up here,
Yeah.
I have the third and final type of the first type of problem.
Yeah, I know.
I don't take a break.
And he needs to explain. Because I don't know.
All right, so here's your third and final. An initial amount of reactant is given, but this time it's a percent to find the change. All of these are, you're given something you have to know. If you have to find K, you have to know all of your equilibrium concentrations. It's just different ways of getting to that point. Do they just give you all your equilibrium concentrations? Well, that's nice if they do, but that's not probably going to happen. Most of the time, they give you an initial amount and then one of your final amounts. And then you just have to do the stoichiometry to figure out what all of the equilibrium concentrations are. This is just a variation of that. So rather than saying what the final product is, they say, okay, a certain percent reacted. So on the problem set that I just gave to you, the packet, not the individual page, you look at 1988, on the bottom problem on the first page, is an example of this, where it says an 89.7 gram, well, first off, at elevated temperatures, SbCl5 decomposes into SbCl3 and Cl2 is shown, there's your equilibrium. An 89.7 gram sample of SbCl5 is placed in an evacuated 15-liter container. What is the concentration in moles per liter? You guys should be able to do that. What is the pressure in atmospheres? You should be able to do that. Let's go ahead and do that. Let's just do it. You need that information to start with, but that's a flashback to the past as far as how to do those. That should be 2 easy points. Great song. He was a one-hit wonder though, I think. So I'm pretty sure y'all can do A1. How do we do A2? I don't know if you heard him. Yep, I'm hearing it.
What's orbiting?
0.0821. I think it tells you the molecular weight. Yeah, it does.
It does tell you the molecular weight. Good. Makes it easy. Okay, you guys finished with both parts?
1 and 2.
1 and 2?
Yes, sir. This is so funny. He was talking to me. This is the driver's ed for me. That was a seat right in front of me. And there's so we had to do the Thanksgiving thing right there. It was so funny. He's like, what's an awareness? And it's second into
I'm anticipating a tennis player coming, asking me for my keys again. All right, how can we shortcut, how can we make a substitution or whatever shortcut on PV equals nRT over V? Without having to go and calculate moles,
take out moles and volume.
is equal to what? N over V, we know N over V is molarity. So it's really MRT, which is going to equal 0.0200 times 0.0821 times the temperature, which is 182 Celsius, but that has to be in Kelvin. 455 K. Okay, so make sure you remember to change that to Kelvin. So the pressure is going to equal how many atmospheres? 0.747. Everybody agree with that number? Okay, so our initial concentration is 0.0200. Our initial pressure is 0.747. So that's a way to give us an initial concentration by asking us to, do other types of problems. So they're mixing different concepts into the same problem, but molarity. But now I know my initial molarity and I know my initial pressure. So now it says calculate Kp or Kc. Well, it depends. Do we want to start with molarity? Do we want to start with pressure? We'll do it both ways just for fun. All right? So my initial molarity of this is 0.020 molar. 0 and 0 of this. Because it says I only put in a sample of this was placed in a container. That's the only thing that was put in the container was this one. So that I have 0 and 0 of this before anything reacts initially. Now I have to figure out my change. Again, if I'm going to calculate K, I have to know all of these at equilibrium. So I have to have some way of knowing my change. Well, my change is going to be how much? 29.2% decomposed. So it's going to be minus 29.2%. 29.2% of what? 0.02. 29.2 of the initial amount. 29.2% of 0.02 of means times is how much reacted. So that's going to end up being 0.0584. 00. So that means that when you subtract that, you're going to end up with 0.01416.
Perfect.
So what's my SbCl3 going to be? Now both of these are plus 0, so we can just go straight to here. These are both going to be what? 0.00584, 0.00584. So then Kc is going to equal 0.0584 squared over 0.01416, and that's going to equal.
Can you not do this?
I can do it on a calculator.
I got 2.4 times 10 to the negative 3.
Okay, here's the keys. Okay, it is this very last key.
Okay, thank you.
Oh, actually, you need the court key, which is gonna be this,
They know which
right
one's
there,
it.
but this is
Where you did this?
And what, 2.4 times 10 to the minus 3. Do we all agree with that? Okay, and again, the unit would be molarity on that one, but we don't care. Well, what if I want to do it in terms of pressure? Everything's got to be exactly the same except the numbers. As soon as that came out of my mouth, I said, well, that may not come out exactly right. But the process is exactly the same. All right, does everybody have this? I'm going to erase this and do the same ice table right here, but in terms of pressure. Okay, so now my initial pressure is 0.747 atmospheres. 0 and 0. But again, 29.2% is going to react, so I'm going to take 29.2% of the 0.747. Which will be 0.747 times 0.292 equals minus 0.218. So then 0.747 minus 0.218 equals 0.529. So that's my equilibrium. Well, what's this going to be? 0.218. So now I go in here, Kp is going to equal 0.218 atmospheres squared divided by 0.529. And that number equals 0.0898. And the unit on that would be atmospheres, but we're not going to worry about it. So we can do it in terms of Kp or Kc. So the percent is going to tell you the exact same thing as if you were given an equilibrium concentration. It uses it to determine what the change is, what the minus X is going to be, so to speak. Yes, sir. I didn't hear a word you just said.
I'm gonna need you after this lesson to explain everything.
Okay, but again, do you understand 29.2% times this equals that number?
Yeah.
Okay, if that's how much reacted, that's why we're subtracting that. That's how much reacted. We started with this, this much reacted, which means we have this much left.
Oh.
So if this much reacted here, for every one of these, we produce one of those and one of those. So if this much reacted, we're going to get that much of each one of those produced.
That and that. Is that and that.
It's stoichiometry. For every one that reacts, you get one made. This is the coefficients.
Okay.
One of these makes one of those and one of those. So if 10 of these react, you're going to get 10 of those and 10 of those. But if we have 100 to start with, and 10 react, we're only going to have 90 at the end. So look at C. What can you do on C? It's more of a thought question, I think. I haven't looked at it lately. Let's not worry about C. Don't worry about C. No, we don't have to do that.
When was the first AP chemistry exam given?
75, I think.
Imagine like being that student and being like, Oh yeah, about to just take an exam and then it's just an AP
Yeah.
knowledge, yeah.
No idea what it's gonna be, no previous questions,
Yeah.
yeah.
Seems fun. Kind of want to do that.
All right.
Imagine like, oh yeah, this is gonna be a breeze, and then you open up and it's just like, I didn't learn this.
Living in the 70s sucks too.
Oh, my teacher never told me that.
Is that a mute button?
I only hear you. He must be talking under his breath.
Yeah, and it's just.
Okay,
Oh, it's smart.
now, this problem here is a flashback to gas laws. I maybe even touched on this one when we did gas laws. But it's a combination of gas laws and equilibrium. So, this decomposition is endothermic, so it gives you this reaction. When heated, it decomposes. This decomposition is endothermic. Make a note of that. So, when I see that, I'm automatically gonna write in heat right here in case I need that later on. They wouldn't tell me that unless they're gonna ask me a question about it later on. So I know that heat goes on the left. A sample of 3.509 grams of SO2 is placed in the vacuum with 1 liter bulb, and the temperature is raised to that. As soon as again I see a gas, I see an amount, I see a volume, I see a temperature, immediately I'm thinking what? Pivner. Okay? What would be the pressure in the bulb if nothing happened? There you go. So A, P is equal to nRT over V. N is going to equal 3.509 grams divided by the molar mass. And they don't give it to you on this one, do they? Okay, so, somebody's getting it? 32.07 plus 32 plus 70.90.
134.97.
134.97 grams per mole. Okay, so that gets me moles. R is always 0.0821. Temperature is 375 K, it's already in Kelvin. Don't add 273 if it's already in Kelvin. And the volume is 1 liter, that makes the math a little bit easier. So my pressure
.800.
0.08.
No, 0.800.
Okay, atmospheres. So that's my initial pressure. So when I'm doing I have 0.800 atmospheres. Now it says, now in part B, this is the part that we did earlier, and we had questions on a test on gas laws. I gave you this type of problem. When the system has come to equilibrium, the total pressure in the bulb. Well, what's contributing to the total pressure? Given that equation up there, what's going to be contributing to the total pressure?
SO2, CO2, SO2.
All three of them, right? So my total pressure, this is again what we have to always remember on this. This is part B. My total pressure is going to be the pressure of the SO2Cl2 plus the pressure of the SO2 plus the pressure of the Cl2. But this is equilibrium, remember, when the system has come to equilibrium. So this is helping me to know my equilibrium pressures. So my total pressure is going to equal, all of it's going to add up to, where's the value? 1.43 atmospheres. But what do I know my change is going to be here? What's my change going to be? What's the relationship?
1 to 1.
It's 1 to 1 to 1. So however much of this is there, I'm going to get that amount because I have 0 and 0, and that amount there. Do y'all remember doing these at all?
Yes.
So then the total pressure is going to be 0.8 minus X plus X plus X. Notice one of the X's will cancel. So X is gonna equal 0.63 atmospheres is equal to X, which is equal to the pressure of the SO2, which is equal to the pressure of the Cl2. At equilibrium, because that says at equilibrium, that's what the pressures are gonna be. So when it gives you total pressure, whose law is that, by the way?
Doyle's.
It starts with a D, but it's not Doyle. You got Boyle
Dalton.
and Dalton. Okay? Dalton's law of partial pressure is what we're applying here. So I know now at equilibrium that I'm gonna have 0.63 atmospheres here, 0.63 atmospheres here, and I'm gonna have minus 0.63, so I'm gonna end up having 0.017 atmospheres here. So now, I want to calculate, it says calculate either KP, calculate the partial pressures, that's what we just did for B. Now C, calculate either KP or KC. Well, it'd be crazy to go and try and do KC, because we have all the pressures. Okay? So, case, this is for part C. KP is just gonna be the pressure, it's gonna be 0.63 atmospheres squared divided by 0.017.
$23.347.
23 point,
347.
well, we'll just say 23 because of two sig figs. All right, I do believe that we went through and did A and B on this problem when we did gas laws. Okay, and this is kind of putting it all together. Key word, key phrase, total pressure. The total pressure is, so this just kind of your ice table is telling me here, okay, it's always gonna, need to know my initial pressure, some of it's gonna react. It's giving me my ice table here. At equilibrium, I'm finding out how much is reacting. 0.8 minus X, X, and X amount. Just plug it in. So go ahead and answer D now though. Maybe you were even interested in seeing your test.
I'm not interested in that.
Could you just not find one singular point?
I tried. I don't like giving 100s.
Was she the first one you graded or the second one?
I think hers might have been the first one I graded. Yeah, I think she's the first one.
I turned it in the wrong place. No, I think he just moved the tests. So like, at one point it was me, Lily, and Sydney all standing up there figuring out how to put it.
Yeah, you weren't looking too.
So
No,
they were
we
all
were-
copying off each other.
No.
I'm just kidding. Yeah, they were confused
Put
with
it
it.
up there, and I was like, there's nowhere to put it. And so
I
she-
know, my entropy just rules in my room.
Yeah.
I clean, and then it just, My desk, if I just quit giving assignments.
Yeah, I
Yeah,
agree.
that's
I agree.
one way.
So are we doing a lab?
Yes.
Make the Black History Project.
I was thinking Friday.
Perfect way to end it.
DECA's gone when?
Wednesday and Thursday.
Of this week?
Yes.
Tomorrow?
and
Thursday. Okay.
And we will be anxiously awaiting your videos.
Wait, you said to me.
Okay, we should be finished with this. This is where the endothermic part comes in. Question D. So endothermic, I know heat's here. So if I increase the temperature, which way is it gonna drive the reaction? To the right, to the right, to the right. So what's that gonna do then to K? Increasing products, decreasing reactants, what happens to K? It increases because it's a ratio of products over reactants. Back in the day when we were out at 3:35, we were almost done. Yes, sir.
So it's increasing. Confusing?
It always goes away from what you're adding. Since heat's over here, it's endothermic. Since we're adding heat, it's gonna shift it that way. Since K is a products over reactants, these are going up, this is going down, numerator's getting bigger, denominator's getting smaller, so K is getting bigger.
Like, shifted the amount of products. So like,
But can you explain the whole shifting thing?
Okay, somebody explain it. So we're at equilibrium. So if I add heat, what happens?
The left side goes down.
The heat jumped on the teeter-totter on this side. Now we're all out of whack. What does the equilibrium have to do to reestablish balance? Well, it's got to go this way to use up the heat and push everything more this way to get back balanced. So we say the reaction shifts right. We're not looking at the initial effect of adding heat. We're looking at what does the reaction have to do to get back to equilibrium. So the heat is the stress, throws it out of equilibrium. The reaction is going to proceed faster to the right, and so until it's rebalanced, then now K is going to be larger than it was before. And temperature, again, is the only one that's going to change K. If I just added more SO2, CO2 gas, it's going to shift right, but the K is going to end up being the same number.
He's relative, or temperature's relative.
Temperature is the only thing that changes the value of K. All right, so those are our three versions of our first type of reaction. It's all about finding my equilibrium concentrations and then plugging those in to find K or Kc or Kp. They just give you all these different ways of finding those initial concentrations. Okay, I don't know how to put that problem into words with the total pressure problem. That's kind of giving you an initial amount and an equilibrium concentration, you know, just the total pressure at equilibrium kind of fits under this kind of category. Okay? So now let's go the opposite direction. Given K, find your equilibrium concentrations. Now we have the single sheet that I gave to you. I'm pushing through y'all. I'm more tired than y'all are.
Oh, brother. Well, you have the authority here to stop.
I know, and I'm not. I could.
That's pretty
I
strong.
could very easily say, y'all just, you know, do some other work. I'm gonna go sit on my desk.
It's all about drive, it's all about power.
Yeah, they stay hungry.
It's all about motivation.
Put in the work.
It's all about, hey,
Put in the hours.
the right thing to do isn't always the easy thing to do. You gotta do the grind.
I love how you didn't like recognize our rock reference just then.
I don't think he's heard the song.
Oh, it's The Rock.
Have you heard the song by Dwayne Rock Johnson?
No, it's not by, he just.
Or like he's
verse.
featured in it.
Rock's verse.
Yeah,
No.
I'll play it for you.
No, that's all right. Okay. So,
It's boring.
yeah.
You'll agree.
It's hot dry.
All right. So given the initial partial pressures, okay, so now we're going to be given the initial partial pressure, and we have to find the equilibrium concentrations. So the partial pressure of the PCl5 is 0.0500 atm. That's initial. The PCl3, 0.150. And the PCl2 is 0.25. And those are all atmospheres. So that's my initial. So now we have change in equilibrium. This time we don't have any equilibrium concentrations, but we're given this, Kp. So I know that Kp is going to equal PCl, this is going to be pressure, the pressure of the PCl3 times the pressure of the Cl2 divided by the pressure of the PCl5. That's my Kp expression. But I know that that all equals 2.15. Somehow, some way, I got to be able to figure out those. Somehow, some way. Well,
Yes.
oh, I didn't realize there was this problem.
What must equal equilibrium? That would be nice.
Go, keep going with this one or change gears. This is a different type of problem.
Is this still AP?
It is AP, and it's still something that we have to do in this unit, but it wasn't the next progression that I was going for.
What if it was each of the rocks on?
Sometimes they give you choices,
Okay.
the right choice. Huh?
You can keep all that on there. We're gonna come back to that.
No.
You actually set it up doing that.
I'm this. I really like this.
Hold on. He's like wonderful guy.
Like, I would rather go to school at 8.
Is it a song that plays like on the radio?
No.
No.
I heard him on the Super Bowl.
You heard about it in the Super Bowl?
No, I heard him do the presentation of the game at the Super Bowl.
I
yeah, that was
didn't even know.
He was very.
It's so funny.
His eyebrow was like nice.
It's a, you know, it's like the halftime show.
That was such a good show. I liked it.
Yeah, halftime show was good for once. It's always bad.
Can I?
It is always bad, I agree. They need to make it to where it suits the ears of people who watch it. I listen to
Gosh,
All right.
Country watched
So
that.
much respect.
51.
Yeah.
51, I'm sorry, this one is called a Q problem. We had to do, the problem with the problem I was just starting is that you have to be able to figure out which way the equilibrium is gonna go. Is it gonna go left to right or right to left? You didn't have a zero anywhere in there, so there's another step to figure that out. Okay, but I don't wanna go there, I wanna do this type of problem first. So number 51, we're given Kc. 2.4 times 10 to the third. We're given our equation, and we're given the initial concentration. We're given the initial concentration of the NO. It's 0.175. And there's 0 and 0 of that. So the question is, what are my equilibrium concentrations? So I have to have my change and equilibrium. Now, we don't know how much it's gonna go, right? So this is where we get to use algebra. This is why you learn how to do algebra,
Oh, shade.
okay? You learn to do algebra so you can apply it in a problem like this. Algebra has a purpose. So, what's the relationship? For every one of these that gets formed, for every plus x and plus x of these that gets formed, how many of these react?
Minus 2x.
Minus 2x. So at equilibrium, I'm going to have 0.175 minus 2x. X and X amount of that. So when I go and plug that into my KC, KC is gonna equal X times X all over 0.175 minus 2X squared. Which means it's gonna be X squared over 0.175 minus 2X squared is all gonna equal 2,400. Now, that looks like a booger.
Oh, we can cross multiply.
Yeah, bingo.
Well, but you're still gonna have a quadratic equation.
I mean, we got calculators though.
Okay, you do have calculators, but just so you know, you're never gonna have to do a quadratic equation on the AP test. But that's why you would just plug it into your calculator if you really wanted to get X. But there's a simple little math trick you can do to make this non-quadratic. Say what?
Square root of.
Take the square root of both sides. Get rid of the square. So take the square root of both sides. So we're gonna end up with X over 0.175 minus 2X is equal to the square root of 2,400. What's the square root of 2,400?
48.98.
48.98. So that would be, let's just say 49.0. Okay? Now we just have to do math. Now you cross multiply, collect like terms, do the algebra. What does X equal?
How many things?
3.
0.0866.
Yeah.
So X is gonna equal these are pressure, these are concentrations, right? X is equal to the concentration of N2, which is gonna equal the concentration of O2, which is gonna equal how much? 0.0866 molar. And then the concentration of my NO is gonna equal 0.175 minus 2 times 0.0866. Actually, I need to do that. Yes, sir.
So, how did you get 0.086?
We just did algebra right here. You just solve for X.
Yeah, but how do you solve for X?
Okay, it's algebra.
I
And you
know
just
you-
multiply both sides by 0.175 minus 2X. That gets rid of that. And then you're gonna have to distribute this times this times that, and then collect like terms.
Okay.
So, what is our final answer? What's the NO equal?
0.0018.
0.0018? Okay, just so we have it. Everybody stay with me, 0.0018 molar. All right. Number 53 is just a fun one. Okay? So, KP is given as this. If the pressure of NO, BR, and NO are equal, what is the equilibrium pressure of BR? So KP is going to equal the pressure of the NO squared times the pressure of the BR2 divided by the pressure of the NOBR squared is all going to equal 0.416. So what's the pressure of the BR2 going to be? They don't give you any numbers other than the 0.416.
0.416.
How's that?
I don't know, just guessing.
Where's the point four?
Right here.
Oh, okay.
If you need to, you follow along in the textbook.
X.
What does it say? Say what? These two are equal, so they're gonna cancel out. So PB, the pressure of the BR2 is just 0.416.
I was right.
Yeah, but you didn't know why.
Oh, that's nice. Or you could like put, since it's equal, be x squared times x over x squared.
Well, that's exactly right.
Yeah. That's nice.
All right. You can stop it.